US Physics Olympiad, year 2022, USAPHO, final round. Problem B3. Time crystal. The kinetic energy E, momentum P, and velocity V of a particle moving in one dimension satisfy F equal delta P over delta T, which is equal to delta E over delta X, and V equal delta E over delta P, where F is the external force. For a free particle, the momentum and energy are related by E equal P square over 2m. However, when an electron moves inside the metal, its interactions with the crystal lattice of positively charged ions lead to a different relationship between momentum and energy. All of the above identifiers still apply, but now suppose that energy as a function of P equal V multiplied by 1 minus cosine Pb, where V and B are constants that depend on the metal. This result is inherently quantum mechanical in origin, and as we will see, it leads to some rather strange behavior. Question A. First we investigate the motion of the electron in general. First, find the velocity as a function of P. Second, the effective mass m of the electron is defined so that it satisfies F equal m star A. Find the effective mass as a function of P. Question B. Now suppose a metal rod of infinite length aligned with the x-axis contains conducting electrons of charge negative E, initially with a zero momentum. At time t equals 0, an electric field E equal E0 multiplied by unit vector x is turned on and is experienced by every electron in the rod. Ignore the interaction of the electrons with each other. First, for an electron that starts at x equals 0 at time equals 0, find its position x as a function of time. Second, if the number of conducting electrons per unit volume is n and the cross-sectional area of the rod is A, find the average current in the rod over a long time. Third, now suppose that every time tau, each electron suffers a collision with the crystal lattice, causing its momentum to reset to 0. In the limit of frequent collisions, charge of electron E multiplied by E0 b tau much less than 1. Find the average current in the rod over a long time. Fourth, if tau can be freely adjusted, estimate the maximum possible average current in the rod up to a dimensionless constant. Solution for question A. First, we investigate the motion of the electron in general. First, find the velocity as a function of P. Solution. Using the provided identity, we have V equal delta E over delta P, and using expression for energy, we have this formula. We need to take first derivative, which will get us formula that V equal big V B sine EB. That was a solution for the first one. Second one. The effective mass m star of the electron is defined so that it satisfies equation F equal m star A. Find the effective mass as a function of P. Solution. By definition, we have force F equal delta P over delta T, which is m star multiplied by acceleration, which is delta v over delta t. So by the chain rule, we have delta p over delta t equal delta p over delta v multiplied by acceleration delta v over delta t, and putting this expression to the first formula and cancelling delta v over delta t, we have m star equal delta p over delta v. But we already know what is the v as a function of p, so we can take reverse function and write this expression, which give us finally this one. So finally m star equal 1 over vb square multiplied by cosine pb. Note that at some points this mass is negative. Applying a forward force can cause an electron to accelerate backwards, which leads to the strange result we will find in part B2. This doesn't contradict conservation of momentum, because the forward momentum ends up imparted to the crystal lattice, causing the solid as a whole to recoil. So that was a solution for second question. So we finished discussion for question A. Solution for question B. Now suppose a metal rod of infinite length aligned with the x-axis contains conducting electrons of charge negative e, initially with a zero momentum. At time t equal 0 and electric field E equal E0 multiplied by unit vector x is turned on and is experienced by every electron in the rod. Ignore the interactions of the electrons with each other. First, for an electron that starts at x equals 0 at time t equals 0, find its position x as a function of time t. Solution. The momentum is force F multiplied by time t, which is negative E multiplied by E0 t. So using the result of part A1, we have V as a function of t equal this expression. Integrating both parts, we have x as a function of t equal this expression, which is solution for the first question. Question 2. If the number of conducting electrons per unit volume is n and the cross-sectional area of the rod is A, find the average current in the rod over a long time. Solution. If we look at this function as a function of t, we can find that electrons just oscillate, not moving further than some kind of fixed region. So it means that the average velocity is 0, therefore the average current they supply is 0. This strange phenomenon is called Bloch oscillation. It doesn't occur in original metals because of the frequent collisions between electrons and ions considered in the parts below. That was solution for the second question in part B. Third, now suppose that every time tau, each electron suffers a collision with the crystal lattice, causing its momentum to reset to 0. In the limit of frequent collisions, E multiplied by E0 b tau much less than 1. Find the average current in the rod over a long time. Solution. For small times, the velocity is approximately this one, where we applied the small angle approximation to the result of part Bi. Thus, if collisions happen every time tau, average velocity is this one. Therefore, the average current, this expression. The plus sign makes sense since it means the current flows parallel to the applied field. That was solution for the third one. Number 4. If tau can be freely adjusted, estimate the maximum possible average current in the rod up to a dimensionless constant. Solution. If tau is small, then more frequent collisions slow down the current, as we show it in part B3. But if tau is very large, then the current cancels itself out due to Bloch oscillations. As we show it in part B2, therefore the highest possible current occurs when the electrons have time to accelerate to a substantial fraction of the maximum possible speed Vb, but collide before their effective mass goes negative. This occurs when E multiplied by E0 tau b is order of 1, and that gives an average current order of Na EVB. Some students try to answer this part using dimensional analysis, but that won't work since there are 5 variables and only 4 independent dimensions: mass, length, time, and charge. Incidentally, you can find the dimensionless coefficient by solving a simple equation numerically, though this wasn't required. That was a solution for all part B, and now we finished discussion for problem B3.